Hi, so we start session 4 of this rank improvement program for JEE Advanced 2020. And as you know that we are discussing one of the very important assignment collection of very good questions. This will be certainly quite useful. So come to the point. We are discussing question number 38. Okay, fine. So one thing you understand here that in this question number 38, please see this one, that which of the following reaction is correct. So you have to understand that uh, the feasibility of the reaction and the course of this reaction. If you see the option A, it is basically the Beckmann's rearrangement, and when this OH group is leaving from this place being protonated, like I say there the OH2 plus because the H plus is there, right? So then there certainly this nitrogen will be having one of the vacant orbitals, so just anti to this whatever group is present that will migrate on this place, and that's why I will say that this one leads to the ring expansion in this case, right? Ring expansion. Okay, and I just write here the product. The product will be, let this 5 member ring as 5 member ring only. Just 1 minute, please. And this one, and this is basically the 6 member ring, right? And initially it's the nitrogen which will be there, and then double bond, and this will be there here, the positive charge, and then the H2 will attack, and so in the place of this the OH group will come, right? I have reduced some of the steps, uh, so you can remove this OH, I mean to say the positive charge, and then tautomerization takes place and you get the product, right? So I mean to say the product will be here the 6 member ring. This one is NH, and this is just the Beckmann's rearrangement, but apparently you will find that one of the carbon is missing in this one, so this one is wrong. Move to the B option. In the B option, HCl is added, and so the H plus is added to this one. This will take here the H plus, and after that this molecule is now like CH3. Okay, and there is positive charge, and here is double bond, and not double bond, this bond, and so what next this ring expansion takes place. Yes, this ring expansion takes place, and so now you will find here the structure little different. Now the CH3 will be here, and double bond comes here. As a result of this, positive charge will come to this place. Here the CH3, and there the CH3, right? Next, what you can do. Anyway, this is also not a stable one, and this is on the ring. So either we can go with this also. In the harsh condition, we can form the double bond. You can say exocyclic. Otherwise, as this is the nucleophilic condition, right? So as per the situation, I can say that there is a hydrogen, so 1,2 hydride shift takes place, and this is coming to new place, right? CH3 double bond, and here the CH3 and the positive charge is here now. Next step, Cl minus attacks, and so this is the product, correct? So B looks correct. If you take this one, option C, let's analyze. C, one thing remember, that this Cl, this place, right, is activated by this NO2. NO2, you know it very well. This is the NO2 structure, and so this is very strong electron withdrawing group, and this one is withdrawing, and so the positive charge comes here, and this HO minus will attack here. This is the Edison elimination mechanism. We say Mason-Hemmer complex, right? So one of the intermediate you can write like this. Just I cleared it. Okay, you can write one of the intermediate. Let the CH3 be here, double bond N, and this one is O minus, and here is the O, and not double bond here, double bond there, and here is Cl, and OH gets connected, that is added. Let the Cl be here, that also remains unaffected, and now, as you know, this is not a stable one, it has lost its aromaticity, and so it is the Cl which is lost from its position, and that is going there, and finally I have started this wrong way. Okay, so I do one thing, I just take we must start from here. This one is coming here, this is coming to this place, this one is here, and this Cl is lost, right? And so the resultant compound is now, I will say, this NO2, right? And let the Cl be here as it is, the Cl will be here in this Cl group, which is activated, right, by this NO2 group, which is very strong electron withdrawing group. So this is substituted. This is basically, this one is Mason-Hemmer complex. This is basically nucleophilic substitution. And it has two methods. One is Edison elimination, other one elimination addition. Already we discussed that reaction yesterday. Okay, thank you. So the C is not looking correct because this Cl is substituted, which is not possible. This is the Cl which will be substituted, right? And come to the next one, D. There the CH3Cl and AlCl3, you know it very well. CH3Cl AlCl3 Friedel-Crafts alkylation reaction takes place, and this is the polyalkylation. And initially there that methyl group will give ortho or the para directing as it is, so on the ortho place and para place, but thermodynamically there that gets rearranged, and we are getting here the mesitylene as the final product. So this is also, you understand that at higher temperature this is not the product, CH3, this is the mesitylene, and this is the final product. Okay, thank you. So this is the question number 38, and for this one, this B is correct, right? Move to the next question. So the next question is this one. Next question 39. Which of the following statements is correct? You know NVS, use of NVS, you know. For what it is known? NVS is known for allylic bromination, right? This is known for allylic bromination, selective allylic bromination, right? And so for that, certainly if I take this process, I will write here, it looks correct only, and so double bond CH2, and this is the perfect allylic place, their radical forms. But very interesting here, you know, that once this kind of free radical forms, this has other canonical form also, and that other canonical form, you see this one is moving here, okay, and so this will go there, right? In the other canonical form is You see other canonical form, you will get like this, where the primary free radical forms and double bond comes here. Here if you see, then you will find that this free radical A is more stable one, and free radical B is less stable one. But when we write the product, corresponding product, okay, let's write here the corresponding product, and the corresponding product is this one, double bond CH2 and there the Br, and its corresponding product is double bond and CH2Br. Now even you can blindly say which one is more stable one, right? And so this one is more stable one. This is called thermodynamic product. Thermodynamic. And this one is the stable product. This one is major product. Yes. So in this case, that has to be the major product written. Now this is not okay. This is not the point here. Here I'm talking about this question, and so this is the product, right? This one is kinetic product, right? Fine. So move to the next option B, right? B, OSCH3 NaNO2HCl. You understand? There the nitrosation takes place, and here para-nitrosation takes place, right? Preferably para-nitrosation takes place here, given the ortho one. So this is not correct. Okay. Even though methyl group is there, then also right now this reaction is very specific, right? Okay. Move to the next question. This is not nothing to explain here in the B option. Move to the next question, C. There you see that how to start, because we have been given one product, and so let's start here. This will be initially this H plus is added to this one, and so this one is now OH2 plus, and this is leaving now. H2 OH2 plus is leaving, right? We have the two options. If the OH2 plus is leaving, then this will be very unstable one, right? Because this will be there. So one thing you understand that the whole scope of this reaction is you will find that it sticks, and that only is the beauty of this question, because initially we start from this place. Here this reaction actually starts from, not from there, actually starts from there. And anyway, you know, there the double bond is more basic than there the oxygen, and that's why the other one is other possible form intermediate. Here you will write, here is the OH, and this one is, now it's better I write here the CH3, and I do one thing, I write here positive charge. Yes, after the addition of H plus, this is CH3 plus. Now you see this one, how good this is. First thing is this one, this is cyclopropyl methyl carbocation. First point, extraordinary stable one. Second thing, after the ring expansion, this becomes extraordinary. You know, just you see this one, that this one is expanding. Then the positive charge comes on this place, where this OH group is stabilizing this positive charge with its extraordinary plus M effect. More than that, their double bond forms, which makes this one very much a stable one. Yes, that leads to the product. Okay, and so now this will be, I write as it is without changing this one. Okay, I write here as it is. Okay, now this one is C double bond O, and you see this one, and there is CH3. Okay, you can write in the decorative way as it is given in the product also. Now this one is C double bond O, this one is CH3. It's true, this is the final product, right? Very nice. Move to the next question. Next option, that is the D option. It's very interesting because you find that NaOET. You know, NaEtO minus is here basically. EtO minus is very strong nucleophile, right? And very strong base also, right? And when it is the ETOH, it is supposed to give elimination, right? So you have not been given elimination, it has been given substitution, and that is also very much possible. The reason is this can be said SN2 prime, right? No? SN2 prime, why? Because even this place, the partial positive charge due to the pulling of this electron is very much stabilized by this one. So this ETO minus is attacking on this place and this will be moving here. And then you will be getting here uh, ETO minus CH2CH and double bond CC2H5 in there the CH3. This is one of the product. In this case we can say, if this is the case, this is the SN2 prime. But honestly speaking, this SN2 prime is not the good you can say the path. Here the major path, as this is project NaOET is project with ETOH, so this is the best for elimination, and elimination is very well possible here right now. And that's why here the E2 path, which is really very prominating here, that is CH2 double bond CH in there the C double bond CH CH3, understand, C2H5 is given, and so there is the CH3. Yes, this is the major product in this case. If ETOH is not there, then ETO minus is best as SN2, and as SN2 we could have taken this SN2 prime path, but as ETOH has been given, so you must understand that E2 is the most prominent path, right? Okay, thank you. We will move to the next question. Yeah, move to the next question. The next question is question number 40. And interesting, what's the question here? Question number 40. What is the question? Identify the reaction involved with intramolecular hydride shift. Good. It is all regarding hydride shift. So let's analyze, because finding one answer is not the target in this discussion. Their learning is the target. Learning is concern. So we'll again discuss all these options. In the A option, you see that chlorobenzene reacts with a chloral CCl3CHO in the presence of H plus. You know the course of this reaction, that very first this one is attacking here. So this is protonated, its electrophilicity is increased. Chlorobenzene will be attacking here, and initially you will get here the Cl. I don't write much in detail. So this will be CHOH in their CL3, right? And now again you see this one, that as it is the acidic condition, so what happens here, that the other chlorobenzene will attack, right? Chlorobenzene attacks. Here is the chlorobenzene. So again this will attack on this place. How this will attack, that also you know, that this will be OH2 plus, this will be leaving, and then this is attacking here, and then you will be getting this kind of product. What is this? Dichloro diphenyl trichloroethene, right? DDT. Yes, dichloro diphenyl trichloroethane. Yes. Okay, option B. Option B, you see this one, what happens here? Here, that's good. This is the question. This is the answer here right now. O minus. This O minus, this negative charge is moving here. This hydride is pushed out from this place and will go here and will reduce this one. Yes. This kind of reaction you have seen very frequently, right? So the reduction takes place and this undergoes oxidation, and you see this one, that is the result of this. So where hydride shift takes place, yes, this is the hydride shift. Okay, so that is done. Then what about C? The C also, it is a Colway's reaction. There the CO2 NaOH. So you know that initially this will be giving here the OH. Again, I don't write here much in detail. This information is enough. And there is the COOH. This is salicylic acid. And then this is treated with AC2O, acetic anhydride. And so this one is O-acetyl salicylic acid. You know, this compound is very important, right? And there the COOH, this compound is very important one. This one is the aspirin, right? Okay, fine. See this question number there, that option D. Option D, CHCl3HO minus. So this one is the Riemann-Diamond reaction, and initially there you will find that this OH group is converted to this phenol, will be having now the CHO on this ortho place. Okay, this is the aromatic aldehyde, and then the acetic anhydride in the presence of CH3CO minus. I hope you remember this reaction, and this reaction is what is this reaction? This reaction is Perkins condensation, right? And so you know it very well. This will be converted to OH, and there is CH double bond, there the CH, in there the C double bond O, and there the OH, right? And again this OH group will be attacking on this COOH. This one is pushed out, right? And then you will be getting this kind of product. Just to see that I write here, this one is 1, this one 2, this one 3. So I can relate here, this one as 1, this one 2, and this one 3, COO, and this is the OH group, right? This is our oxygen. Yes. Okay, fine. So our answer is B. Okay, we'll move to the next question. So the next question is 41. Okay, and when N-butanol is reacted with excess of formaldehyde in the presence of concentrated alkali, the major product obtained are. I hope you got the question. This one is you see, write this one, when N-butanol, I mean to say N-butanol, it means CH3, CH2, CH2, CHO, reacts with excess of formaldehyde, HCHO, HO minus in excess. What is this reaction? Initially, aldol condensation. It is not condensation but aldol, right? So HO minus, you know that HO minus will attack here, this alpha place, and then you write here its tautomeric form, and that is CH3, CH2, CH double bond, CH in O minus, this will form. This is the enolate of this, right? This enolate will be acting as a nucleophile and attacking over the SCHO. So that is attacking over the HC double bond O, and there the H. So this one is moving here. It is not the oxygen which will attack. then this one is moving here, and from there it attacks on this place, and this one is added. And as a result of this, what we are getting, the CH3 CH2, and there the CH, and this one is now CH2 OH, that's right, and there that CH double bond O, right. HO minus is reproduced, right. HO minus is reproduced, that is acting as a catalyst, right, and so that HO minus will attack again on this place, right. HO minus is attacking again, that will form carbanion, right. So you will be getting now CH3 CH2 C minus, in there the CH double bond O, in there the CH2OH. I could have written here that double bond CHO minus, but one thing, this is the place where the dehydration takes place through even CB path. But instead of dehydration, as SCHO is excess in excess, so what happens here? This one is attacking over the other SCHO. That only is the beauty of this question. And so this minus is attacking on this one, this will turn up, and another addition takes place. And with this one we are getting here the CH3 CH2, in there the CH2OH, in there the CH double bond O, and CH2OH. Yes, it happens. Now the best part, again there the HO minus is reproduced, and SCHO is still in excess. What we have done, the aldol condenses, instead of condensation, aldol, you can say that addition, the addition part of the aldol happened. Now I hope you understand why I don't say condensation, because there is no dehydration. Dehydration is the essential part to be called condensation. So as here dehydration does take place, that's why it is not right to say. Aldol condensation has two parts, nucleophilic addition and following dehydration, that is basically condensation, right? So in this case, now we find that very good situation, that where SCHO is still present, SCHO, in there that HO minus is still present, and this is very ideal condition for a cross Cannizzaro reaction. Yes, this is the cross Cannizzaro reaction. Very ideal condition, because this compound is also non-ionizable, and this SCHO is certainly non-ionizable, and as SCHO is the best hydride acceptor, so what happens here, you can say this, here I can say that this is more prone for the oxidation, correct. So this will be oxidized, and this CHO gets reduced, right. So this is the best hydride acceptor, but here this is not the point of the hydride acceptor here, which takes here the HO minus, that is important, right. So the product is finally CH3 CH2C CH2OH, here the CH2OH, and this CHO is now reduced to CH2OH, and this SCHO is oxidized to HC double bond O minus. These are the final products, and this whole process is called Tollens condensation. Tollens condensation. What is this? Aldol addition followed by this Cannizzaro, cross Cannizzaro reaction, right. Okay, fine, move to the next question. Question number 42. Okay, question number 42, which of the following is incorrect? Again you have to understand, this is primary amine CH2NH2, and that reacts with NaNO2HCl. This is known for diazotization, right. So go for the digitization. I write here. Here is the OH, CH2, and there the N triple bond N plus. I don't write much in detail. You know that NH2 is converted to N2 plus, which is acting as a very good leaving group now, and so this one is moving here, and this the resultant carbocation is stabilized by this OH group, and so this one is, yes, cyclohexanone. Right, good. You have to find incorrect. So this one is correct only, right? Second one, CH3, CH2, COCH3 that reacts with the NaNO2 HCl. Okay. So NaNO2 HCl, again, that is the source of NO plus. Here there is no NH2. That's why we are not going for diazotization. Diazotization kind of thing is not possible, but NO plus is the electrophile, and so here initially you will get here the electrophilic substitution. Let's take here, understand this one, that this compound initially gets converted to CH3, CH double bond C, and there the OH tautomerization takes place. This is the thermodynamic tautomerization in the acidic condition. You know it very well. And so when there the NO plus is present, then again this one is moving here, this will be here in attack over this, and finally we are getting CH3, CH, and there the N double bond O, C double bond OCH3. That is true. Next, you see what happens here. NO is there, in its alpha place there is hydrogen, so this is the best for tautomerization, better tautomerization, and tautomerization takes place here. This hydrogen is lost, and then this will come over this, and so the final product you will find here, the CH3C double bond N and OH, and C double bond OCH3, right? Exactly correct. Fine. So this is also correct. So what about the C? C is apparently wrong. I hope you know this reaction, because when CH3COCH3 acetone is treated with Mg in ether following treatment of H plus, it gives pinocol. The product is not this one. Product is here. It is not the product. Product is CH3C, CH3 and OH, CCH3. You know the mechanism we discussed earlier, right? So pinocol forms. Mg will give here the two electrons. One there, this will be O minus, and their electron, both free radicals will combine together in O minus, further protonation, and pinocol is the product. Fine. So this one is the wrong one, right? D option also you see. This is the anthranilic acid, in that reacts with NaNO2 HCl. One thing is very clear now, that this NaNO2 HCl will convert this into N2 plus, and this one is C double bond OOH. It's very interesting that their decarboxylation takes place, because N2 is the leaving one, right? So this one is moving here, this one is moving here, that is lost, and finally we are getting here this kind of benzene. If there is something to accept, this will be merged with that one. If not, then this kind of unstable benzene usually undergo dimerization, and with that dimerization, that gives this one, right? So this is also correct only, right? So next question is 43. Which of the following is not correct? Okay, so you see this one, this compound is treated with NaOET, ETO minus base. Okay, and apparently it appears that this reaction is Favorsky rearrangement, right? What is this? This is Favorsky rearrangement. I hope you are clear now. So this ETO minus base is attacking on this one, and you will get here CH2 minus C double bond O CCH3 CH3. Understand this question, this reaction. Cl is here. Now this negative charge from the other side will attack here and push it out. As a result of this, what we are getting? One cyclic 3-membered ring, CH2 C double bond O, and there the C CH3, and there the CH3, like this. Okay. Now again ETO minus will attack. This ETO minus attacks again on this C double bond O. This will go up. So you are getting now CH2C, and this one is O minus in OET. Okay, there the CCH3, and there the CH3, right? This is not a stable compound, so this O minus will be trying to get its more stable status back, and then one of the bond has to go back, right? Now which one? Certainly which will give you the more stable intermediate like CH2 minus, and this is the right place, and because of that we are getting now CH2 minus, and there that CH3 there CH3 CH3 C double bond O OET, right? Yes, protonation takes place. You take the next step, and the final product is CH3CCH3, and there the CH3 C double bond O and OET, right? Then so this one is correct only. Next one, option B you see. Br2, this ketone reacts with Br2CH3COOH. One thing you understand that tautomerization takes, this is electrophilic substitution, alpha halogenation, and you have already learned that if this is the basic medium, then there a strong basic medium, then kinetic product is the major one, otherwise thermodynamic one. So when we'll take here in the acidic medium, certainly all these things will be happening based on the more stable there the enol, and this one is the CH3, this one is the thermodynamic enol, based on this So when there the Br2, so this one is back, this will be here, this will attack here, this one is lost, and so this time in the presence of this Br2CH3COH, Br2 in the presence of CH3COOH acidic medium, there the product will be this one. This could be the product, I write here. If you take here the HO minus, otherwise if you take here LDA, strong base, even there if you take here the HO minus, NH2 minus, RO minus, as the strength increases, the yield of this kind of kinetic one increases, right? So okay, fine. So certainly this is not the appropriate one, not correct, so this is not correct. Okay, fine. Let's take here the option C. Option C, just now we have discussed, this one is the Beckmann's rearrangement, and this OH very first here this OH will be protonated, and then this one is leaving, and from the back of this, from the anti-place, the group migrates. So it is the CH3 what migrates, and I just write here. Here you will get PHC plus double bond, and in there the CH3. Okay, and then again there the H2 attacks. You know it. You will be getting here PHCOH double bond and CH3. So after tautomerization, we are getting PHC double bond O and HCH3. Yes, this is the correct one. Okay. Next one is NH2CH3COCl. Right. So CH3COCl, this reaction nucleophilic substitution takes place. This one is attacking here, the Cl is substituted, and you are getting initially NHC double bond O CH3, there is NH2, you know this. So this will be attacking here in the next step, and this is the nucleophilic addition, and as a result of this you get NH, now C OH. For the better clarification, I write here all these things, NH in this one, but this is the right place for the dehydration, so this will be the aromatic one, aromaticity, and so dehydration takes place, and we get very good compound. Final compound is NH N double bond in CH3. Yes, you see this is the final product. Okay, next question is 44. Okay, so very interesting. Which of the following reaction is not correct? Okay, CH3CO, CH2CO, CH3. This is 1,4 diketo compound. If 1,4 diketo compound, certainly this one is wrong, right? Because it gives. We discussed this in this mechanism, and so this will be giving here the CH3, and there the NH CH3. This kind of parallel derivative, right? This is the compound, cyclic. Next, option B. So CH3CH2COO Ag reacts with I2CCl4. That gives ester. Yes, this is correct one. Already we discussed that in the case of Br2. If there is a Br2 CCl4, there that lower bromide forms in the Hunts-Dicker reaction. This is the Hunts-Dicker Burn-Bonds-Simonini reaction, where that little change in the ratio gives this ester. So, okay, ester forms in this case. See, something looks wrong here because CH3C, CH3 double bond CH, this is the hydroborational hydration, and if there is the hydroborational hydration of this molecule, there is some printing mistake either this side or that side, either the place of the double bond or there the place of the OH, because it is very clear that CH3CCH3 as anti-Markovnikov's Edison hydration. So this will be H in there, the CH, OH and CH2CH3 is the product. D option is also the same one. We are taking here the selective reduction. We are taking here the selective reduction. For that we are using here dicyamyl borane, that is hindered one, and that will reduce the double bond preferably which is less hindered, and certainly this one is less hindered. So that is reduced. Okay, so move to the next question. Question number 45. Okay, interesting. Here there is full chance of mistake. Okay, question number 45, even you know it very well because you see this one. First ozonolysis takes place. Ozonolysis means there the cleavage. What do you get here? You get here C double bond O, C double bond O in this one, and the similar thing there also, double bond O, this side also, double bond O. This one is the initial product. What next? Next is there that is treated with Cl2HO minus in certain indexes. This one is COCH3. This is the place where there is chance of mistake. So this is the chloroform reaction, and you know it very well that in this case there the cleavage takes place, right? And so finally you are getting here C double bond O minus. Should I write here there that first one, second one, there the H plus, I include there the H plus also, and we write here the H plus. Okay, and this one is C double bond O and OH. One carbon is missing here. Just I did something just to take this one. So this one is C double bond O, OH, like this. Correct. C double bond O and OH, C double bond O, OH, C double bond O and OH. Okay, so which is the right one? C is the correct one. Done. There is no problem at all. Move to the next question. 45 to 46. Similar question, but that is treated with KMnO4H plus. Okay, so that is also the oxidative cleavage. One thing, when di-substituted double bond is oxidized, we get ketone only. So initial product what will be there, that will be similar one. I write here C double bond O take C double bond O, C double bond O, like this. This only is the initial product. But what is the purpose of this question, right? Purpose of this question is little different, looks little different, because KM4 H plus in heat also given. So this one is this implies here you can say in extreme condition, right? It implies here the extreme condition. Extreme condition, or I can say that there that as heat has been given, in that case even the ketones are oxidized, oxidative cleavage takes place. For that we discussed Popov's rule also, right? So the further cleavage takes place, and because of this you will be getting the oxidation like this here, the oxidative cleavage, and so CH3COOH, CH3COH, 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 in this part also COH. So actual compound will be here now. This one is C double bond O, in there that OH, C double bond O, in there the OH, C double bond O, in OH, C double bond O, in there the OH. Now you see this one, there is a heating condition, the two CH groups are present on the same carbon atom. So initially, stepwise I am writing here, there is C double bond O, OH, C double bond O, in there the OH, let it be there. In this one already I have explained you. This is the beta gamma unsaturation, easily decarboxylation takes place, and this will be finally C double bond O in OH. Same thing will be repeated other side also, because this is also this one is alpha, this one is beta, this one is gamma, and so we find double bond in between double beta and gamma. Decarboxylation will take place very easily, and so I write here this side also. This will be C double bond O and OH. This will be there. CH2, in there the C double bond O, in there the OH. This is the CH2 now after the decarboxylation, right? And so this again beta gamma unsaturation, because this one is alpha, this one is beta, this one is gamma. So this is the extensive reaction, right? And finally we are getting CH3, C double bond O, and OH. Yes, if this is the case, then this is the final product, right? This is very interesting, and here you need to understand the basic purpose of this question. Otherwise, even if a single question, small question, simple question, you can take to this level and you can spoil also. Okay.